All right, hello and welcome again. I'm glad you're here. This is the robot foot in Keyshot. I just like the foot. I think it's cool. These are some of the parts that I had written in the cubic inches um, as texture files to put the robot together. And what we're working on is a CNC discussion of what I'm trying to do to establish a way to give these robots the ability to really truly mimic a human being based on the use of hydraulic cylinders. And of course, I always want to add this. And again, I do have a YouTube channel, and I have a website and a web page. This will be under that. I'm not sure this exact video will be, but the topic of the hydraulic cylinders will. And we're talking about creating a physically real item. I want to demonstrate that I am correct about these hydraulic cylinders, but it is a real structure that has fluid and pressure in it, and that is an element. It's a pressure vessel. Any physically real object could potentially hurt somebody. And my advice is, if you are managing a physically real item, you should manage it in a manner that is legally allowed and reasonable and safe. And if you cannot manage it in that manner, then it is my advice that you do not create it as a physically real item. And now we'll go look at some other things. And I do this on my desktop. I always like to see what is going on. This is Serrano in Tuscany. I like this. See, in this house, whoever, they've got their clothing out on the line, but that's red and yellow and warm and saying, yeah, come on in and visit. Tell me about your robot. And over here, it's blue and cold and purple. These are the people where they're saying, I'm not sure I understand what you're trying to say. And actually, I have the impression I'm not sure what I'm trying to say. So I'll go head back down here to these people who like me. It's just a thought. Italy. All right, let's take a look at some of the drawings. And we will take the robots and tell them thank you. Thank you for parading around and showing us how skillful you are as robots. And let's look at the drawing files. And I know there's always an interest in the drawings. And I don't mind the drawings, but I don't think this makes a whole lot of sense if I don't first get out what it is that I'm talking about. What is the issue? And this to me is just a flow diagram of what's going on with the modern way that they work with robots. And these are human beings that send information to the computer inside the robot, and these people are telling the robot what they want it to do. And the robot central processing unit runs calculations and looks at its algorithms and makes these requests into actual physical commands from the central processing unit. And these commands are then sent over a network inside the robot to the prime movers of the robot. And these are commands for these prime movers to do something, move something, and they do. And when they make these motions of themselves, they move the robot, and that movement of the robot is noticed by the sensory system, because the sensory system is always monitoring the robot. sensing what's going on, preparing a package of data of the status of the robot, and sending that package of digitized sensory data back up to the central processing unit saying this is what has just happened to the robot. And then the central processing unit takes a look at what is the real status of the robot and what is the status of the robot that the central processing unit would like to have. And based on those two different situations, almost always, the central processing unit will run its algorithms and come up with a new set of commands that it sends out. And this loop just goes around and around and around like this. And that's what's going on. And the issue that I'm discussing is that hydraulic cylinders, on a very specific topic of human mimicking robots, if you want to mimic a human being in terms of the power, the strength, the speed, the fluidity, the grace, the beauty of human motion, particularly with a 6-foot-tall robot that weighs 180 pounds, you're not going to do that with electric motor gearhead systems by themselves because they don't have enough power. And in the hydraulic cylinder sensory world, you need measurement of the extension and retraction of the piston rod, because that's how the sensory system useful to the central processing unit will want information from the hydraulic cylinders. And it needs to be reliable, accurate, rapidly, repeatedly updated. It has to be created and then converted into digital information that can be sent out over a network so that it can go from the sensor to the central processing unit. The sensory equipment has to be inside the cylinder structure of the hydraulic cylinder, because the hydraulic cylinder itself is made of metal and strong and thick, and there's no extra clearances in there, and you can't put your sensory equipment outside of the hydraulic cylinder and have it sense what's going on inside the hydraulic cylinder. That's too complicated and too expensive. I think what we need to do is create a polymer bushing material inside the hydraulic cylinder, because the space inside the polymer bushing material is a space where we can put our sensory equipment. And what I want to do, first thing, is to show that the polymer bushing material can be the cylinder of a hydraulic cylinder. So we need to have a functioning hydraulic cylinder where the cylinder structure is made of the polymer bushing material. And I guess I should take a look at a hydraulic cylinder real quick. And this is the robot. Now, this is back when the robot didn't have arms. But this entire structure is a hydraulic cylinder. And the hydraulic cylinder has a connector on one end. It has an end cap on one end. It has what I call and this is me just making up definitions, but I'm going to call this structure here the body, or the cylinder body, of the hydraulic cylinder. So this is not the hydraulic cylinder. This is just the cylinder body, but it's this body that I think needs to be made out of the polymer bushing material. And this entire structure is actually a hydraulic cylinder under the mechanical engineering concepts. And we'll go back to where we were. And it's the drawings, the drawings, the drawings. Where are the drawings? Where are they? But I wanted to say a few things about creating something. And I did surgery for a while, for years. And one thing about surgery, you put someone to sleep, you cut them open, you go in there and work around, you get everything the way it needs to be and fix the problem, sew it all back up again, wake them up, you come up there and talk to them, and the next day in the morning you're like, well, you know, I've been thinking about what I did and I'm not so sure I like it. And so my thinking here would be, let's take you back to the operating room, put you to sleep again, cut you open, and mess around in there, put it all back together again, and let's see how that works. And it's you can intuitively understand about human beings is they do not want to do that. And so my approach to these concepts of creating and working with physical parts is I don't want to make it 3 times. I don't want to fix it. I don't want to test it. It doesn't work. Throw it away. Make another one. Modify that. See what it does. Throw it away. I don't want to do that. I want to think about it and consider it and ruminate and then create it. And the very first time I create it, I want it to work perfectly. So I know the mechanical people are just like, yeah, well, dream on. But I think you can do that as long as you have that as a point of view. And what I want most of all is that it will demonstrate what I'm trying to demonstrate. I want it to work. And the outcome I'm looking at is Delrin, the polymer of formaldehyde, polyoxymethylene, which is created apparently initially by DuPont, and they named it Delrin, that plastic polymer material could be the cylinder body of a hydraulic cylinder. I do want it that this is not expensive because I have to pay for it. It's remarkable to me that the robot people just have no interest. It's weird, but that's another story. I don't think when we're fabricating structures out of metal that we should have parts of it that are sharp enough to cut the human skin. I know I'm going to have to put it together and take it apart and put it together and take it apart because I'm testing things. And an absolutely perfect machined right angle, that edge is sharp enough to cut a finger, I think. And so I'm hoping for mostly rounded edges. Also, every accident I took care of with human beings, they didn't wake up and say, well, today I'm going to go have a car accident and let's see what happens. So I'm not planning to drop this thing. I'm not going to work on it over concrete, but there's always a chance it could slip out of my hand and fall onto the table or maybe fall onto the floor. I don't want it to be so delicate and so carefully constructed that if it slips and falls, it breaks, or it slips, it falls, it hits the table or the floor, and some part of it bends and makes the whole thing not work. I don't want to do that. I've been surprised with respect to making a hydraulically pressurized device that will not leak. The people that make seal up things, seal it so it won't, not sealing like the thing at the top of your room, but seal it up so it won't leak fluid. They are very, very, very specific about how to do this. And I think hydraulics have been around for 140 years. And they don't want people mad at them. And sometimes what's inside pressurized hydraulic systems are materials that are expensive or valuable or dangerous or reactive, and they don't want it to leak. And they're like, if you will listen to us, it won't leak. And thus, features of this device related to sealing it so it won't leak fluid, I think those features have to be pretty specific. The rest of the dimensions of this structure are simply, I just said, well, how does that look? That seems okay. I wanted to have rounded edges. I wanted to have enough thickness that it won't break. But he's happy to defer. I don't run CNC machines. And somebody might say, yeah, well, we can make what you said and it will cost $47. But if you will just listen to us, we're going to keep all the sealing features so it doesn't leak. But if you let us do this and that, we can make it for $8. And I'm going to say, yeah, that's okay with me. And in terms of, well, it might be $8, but it's not going to be this beautiful piece of jewelry that you have created. And my opinion is, I don't care what it looks like. I just want it to work. I do want the hydraulic fluid in it to be water because I want something that's non-toxic, available, safe, inexpensive. I do think I'm going to have to put it together and take it apart and put it in. And it spills out all of its hydraulic fluid. Well, what do I care? I can go over to the sink and fill a glass up with water, a plastic cup up with water, and refill it. I like putting mechanical parts together where, if at all possible, I would like there to be bolts, and the bolts are connected to nuts, and the nut and the bolt are screwed together, and that squeezing force is what puts the object together. And the purpose of that is when you have a very valuable metal object that is important and you paid for it and created it, and you have to put a bolt in there and tighten it, if you strip it, you've wrecked it. On the other hand, if you put a bolt and a nut in there and somehow you manage to strip it, you have stripped the bolt. And you just back it all off or cut the bolt and get another one. And you haven't really done anything to your structure. So these are just some design priorities. I thought I would bring those points out to have that there. All right, so now we can do some discussion about sealing. And again, that's SEAL, not the ceiling up above your head. And the issues associated with sealing, now the hydraulic equipment has been around for 150 years or more. And what happens is words that describe things are there, and then different words are used, and then different words are used, and then hydraulics are used for the concept of a valve and to seal a valve, and then they're used for construction equipment. And what happens is all of these parts have a variety of different names, and they're all talking about the same thing. And I don't mind that. It's just weird. And so this is the piston rod that goes back and forth, and this is the thing that the piston rod is going back and forth in. And sometimes they call this a gland, G-L-A-N-D, and sometimes they call it a housing, and sometimes they don't say what it is. But this is the part that's moving back and forth. This is the part that's not. And the issues that are associated with this are something. So the hydraulic fluid is in here, and the hydraulic fluid wants to leak out. So they put something in here to keep the hydraulic fluid from leaking out. But the other thing that matters is this is metal, and it has to be taken to a very fine roughness. This is the piston rod. And you don't want the piston rod to run into the housing, because if it does, then the housing will scratch the piston rod. And once the piston rod is scratched, that scratch acts like a plow that just digs apart this soft seal and ruins it. So the hydraulic sealing system for moving parts is actually built in two parts. One part is the soft, flexible sealing material that keeps the fluid from leaking out, but there's another part in here that they call a bearing or a spacer or a bunch of other words. And this thing is a padding material that prevents the piston rod from running into the housing. And that just goes on and on and on. And then they have specifications for, not only is it important what the dimensions are, but it's important what the radiuses are and what radiuses are allowed. And the final thing that's important is what is the roughness of the edges. And those are three separate issues. And I'm going to use a O big D. That's sort of the diameter of the hydraulic cylinder. And this is the diameter of the rod. And so the rod I'm going to use is a 1/2 inch in diameter. And the piston, the cylinder, is going to be 1 inch in diameter, inside diameter. So you have to go find 0 little d, 1/2 inch, and it gives you tolerances, and it gives you about how big this distance is that this seal is going to fit into. and it gives you the length of this. And then you'll notice that the length of this is 0.187, but this is what they call a groove. Like I said, all of this technology, names and conventions of how they say things goes back forever. This is the groove, and this is the length of the groove. So the SL, the seal length for a half-inch seal is 0.187, but the groove length is 0.207. You'll notice all of these are accurate to 3 places, so they're not kidding. This stuff, it's very important that it's just done just right. Now, there's a thing called extrusion, and I think I'll get to that, but extrusion is where the pressure is enough that it starts pushing the seal into this. Okay, here's the piston rod, here's the housing, here's the seal, and it pushes the seal into this space right here, and that's called an extrusion, and that breaks this and ruins it. And this distance is called the maximum allowed extrusion distance, and this distance has to be small enough that if the pressure you're working with will not ruin your seal. And so they give you, this is from halite, and halite is all over the place, including Asia. So yay, I think we can get these parts and have them mail. I might be able to go to Amazon and put your address in there. But this is the halite 605 rod seal, twin lip polyurethane, can be used in water. And what they give here is and this I think is like 3,000 pounds per square inch, and I'm going to be way down here at 20 pounds per square inch. But the 605 can have an extrusion gap in millimeters, and I picked 0.5 millimeters, and I work in America, and we use those numbers that Americans use. So we'll convert millimeters to inches. And so 0.5, and this is the way it goes. This goes on and on and on like this, but 0.5 millimeters is 0.01968 inches. And we're going to see this number over and over again. All right. So now, one of the things that I did a whole different bunch of ways that I tried to design this, and I'm going to get back to all that. But I do these are screen captures where I took a picture of what I found on the internet. And I did want to show you that I made for you a PDF document, 72 megabytes, of all of these screen captures. And we'll go see what that looks like. And this is it's showing here in my Adobe, but it's a collection of 42 screen captures. So you can see over here, well, it's big enough. Another thing, Adobe is always trying to help you, and I wish they would stop helping, but they don't. But anyway, see, so there is page 2, and this is the for that 605, it's the dynamic sealing face, the roughness, the static faces, the roughness, the chamfer, the minimum. These are tolerances. These are specifications that exist for this equipment, and these are just, it goes on and on and on. And what I'm showing you is just all of the different screen captures that I have, so that you can learn about this sealing issue without having, you can go out on the internet. All of this is free, but I just thought I would show you all this. And here they go over the surfaces and on and on. Okay, so that's what this is. And just it's more than you ever wanted to know about sealing. But this, I'm going to put this in the G drive so you can download this collection of PDF. And these are nothing more than just screen captures of things that I found that I thought, like here, for example, this is the fluid seal, and the red is surface roughness. So RA of 30. And the brownish gold is guide rings and wipers, 63. The axial face of grooves, that's the sides, 125. So that's useful. All of this stuff, it just goes on and on. And if you don't do it exactly the way they told you to do it, then their opinion is it's going to leak. So that's why I'm going into this level, this issue. All right, so here, and the final thing I'll cover here, this is the piston rod. And the piston rod can bounce up and down inside the housing. Okay? But they don't want the piston rod to run into the housing. So they have this padding material. And the question becomes, say the piston rod went down and ran into the padding material. What has happened is this distance has increased. Okay? And this distance from here to here is your extrusion distance. And so you can't exceed the extrusion distance. And what this means is a set of very complex ways of thinking. But basically, this is the padding material they call the bearing or the spacer. And the amount of the bearing that sticks out of the housing needs to be 1/2 of the minimum extrusion or the maximum extrusion distance. So that if the piston rod thumps itself down this way, when it runs into this, the distance that's up here, so this piston rod was touching that, and now it's down here, but the distance has become equal to the maximum extrusion distance. And so you get these collection of distances, like the rod diameter, the maximum extrusion distance, 1/2 times the maximum extrusion distance, the bearing thickness minus 1/2. Okay, so the bearing thickness of 0.062 inches, that's this distance from here to here. The bearing sticks out by a distance equal to 1/2 of the maximum extrusion distance, which is 0.00984 inches. So this distance from here to here is 0.00984 inches, and that means that this distance from here to here is the thickness of the padding minus how far it sticks out. And I know you are going, who cares? What difference does it make? But there's no way to figure out the distance from here to there without doing these calculations. And you have to create in your housing this groove where this padding goes. And so there you go. And it's one of those things where if you like math, if you don't like math, you start pulling your hair out. But this is the beginning of me showing you what I was thinking to do to create this device. And this is a clamp that fits onto this Delrin cylinder and pulls it. And this is the clamp that has the halite 506 bearing material and the halite 605 sealing material. And this is what's called a split gland. Otherwise, you have to take your fingers and try to push this thing up into this groove, which I don't think I can do. So this way, you take this here, get it out of the way, you push this on here, and then you bring this back. And so this is the square cross-section gasket, which they call an O-ring, although I always thought an O is an O, but this is considered an O-ring. It's just a square cross-section O-ring. And what happens is when you take this nut and bolt and pull it tight, this has grabbed onto the dowel ring and it squeezes the dowel ring up against this, and this square cross-section is squeezed into this shape. That took a long time for me to get that straight. That's just amazing. And this is called a 1/8 inch square cross-section O-ring, even though 1/8 is 0.125. The convention is, and I'll just do one thing right here. 13.9. This is times 10. My drawing program works better times 10. So remember that. But the 0.125 1/8 inch square cross-section O-ring is actually 0.139. And again, I think this is because it goes back 150 years. But this square cross-section, once this is clamped on here, assumes this cross-section. And since it assumes this cross-section, this groove has to be of this shape so that this thing is squeezed into a size so that the, and I hope this is right, but if you look at this, at millimeters squared, 124/651, and we can hope. I hope I did this right. All right, I'm going to try to give you a conversation about how complicated this is. And I know you might be thinking, why is this so complicated? But I think it's because the people who do the sealing, again, they don't want it to leak. They don't want something to go wrong. They don't want materials leaking out that are valuable or dangerous. So we're talking about, this is the dowel ring, and this orange piece grabbed a hold of it and is going to push it this way. And in here is this 1/8 inch square cross-section O-ring seal. And again, I think I'm on times 100 here, so it's times 10. So it's not 0.125, which is an 1/8 inch. It's 0.139. Where that came from, I don't know. But that's what it is. But that's what it's going to look like when it's not in its compressed condition. So that's important to remember. And you'll notice that I'm showing that this nut has been pulled out. So it's not compressing it. And this orange, this pulling part, has not pulled this against that. And when it, notice that this orange has jammed its little teeth down into the dowel ring. So when the orange goes this way, and the orange will go this way because someone tightened this nut, it will take this orange and this dowel ring and will push it that way. And it will push this square cross-section O-ring up against this housing. And so we'll go, now I want you to see, here is the PDF. It's 41 pages. So all the way down here on page 41 is all this information about these seals. And that's page 41 of your PDF. And this is page 98 of this Parker Hannifin document. And it gives you all this stuff that you have to have, like the groove itself, the particulars of the groove. This can be 5 degrees off. This radius can be 0.005 inches. This surface roughness is 63 RA. And this surface roughness is for liquids 32 RA. So it just goes on and on and on. And then the other thing we can look at, we are using a 1/8 inch square cross section O-ring, even though it's not 1/8 inch, it's 0.139. And it's the Parker Hannifin 201 through 284 series. And so they give acceptable values for the depth of the gland, the amount of squeeze, the groove width, and the R groove radius. I guess that's this radius up here. Okay? So now we need to go, we take all these numbers that we have, and this is in your PDF. So we're going to take all these numbers and compare them to the actual drawing that I've prepared. And you will see that this is part of the design of this thing where there's not a whole lot. Well, I have to be careful. As long as it's not too expensive, we should do what they're saying. If this thing starts to get too expensive, this will take it up to 1,500 or 1,800 pounds per square inch. I'm only going to put 20 on there. So it may be that we need to back down some of these dimensions and specifications in order to keep this device from getting too expensive. It's my hope that you just dial in what you want to the machine and close the door and go outside and eat lunch. And after an hour, you go back in there and open the door and it hands it to you. That's what I'm hoping. That, in other words, all these dimensions, the machine just doesn't care. It's like whatever you want. And it's not any real work. Somehow. And all projects that occur inside of my mind are always simple. I'm hoping that it's that simple in reality. All right, so this is your PDF that you will have, page 41. And now we're going to go look at the actually real document. This is the internet here, okay? So this is 292 pages of Parker telling you more than you would ever want to know about O-rings. And we can go to page 98 and we see this, and we can plus it up a little bit, and you will see that this page is the same page as the page I just showed you, except this is the actual real authentic internet connection. You can go to this internet address and find this. And so the way this, okay, and so now we're going to go back over here into my drawing in SketchUp. And here it is pulled apart. And we're going to go down here. And so this is the shape of this. Oh, and I should show you, I found, and this, I'll show you this in your PDF file. So this is your PDF file, and we can go up. This is this thing about extrusion. This is what they're worried about. And that I'm going to talk about a little bit more on the, remember, this is the static seal. This is not the dynamic seal, but we can keep going up. Here it is, right there. So this is a product that's available for $17. I can give you 50 of these things. I'm hoping I can get on Amazon. I did this with my son one time. and just have Amazon send it to your company. But there it is, actual 0.139. Water. Inside diameter, 1 inch. 0.984. It's good. It'll be stretched a little bit. That's okay. So there it is. So that really exists as a real item. And this again is page 36 of your PDF. So we'll go back over here. And so this is this structure. And then down here, we took our wrench, we put an Allen wrench on this socket head screw, brass, and we pulled the nut down, and the nut pulled on this orange thing, and this orange thing is pulling on the dowel ring, and it squeezed the dowel ring. I mean, the dowel ring itself squeezed the O-ring. So the O-ring went from this shape to that shape. And we can see here that the cross-sectional area of this, okay, so this is times 10, 0.139 by 0.139, cross-sectional area of, I think it's 0.019 on the real one, but it's 1.932. And then we go over here to the new shape that it took on when we squeezed on it, and it's 1.932. So this amount of rubber can become that amount of rubber, or this shape can convert itself from this shape into that shape, and you don't have to remove any rubber. So that's important. Okay. And so as we squeeze this thing down, this dowel ring started mashing on this O-ring, and this dowel ring squeezed this O-ring out into this groove. And the only thing we have to do with this groove is reassure ourselves that we're doing okay. And these are some of the things that we want to look at to be sure that this groove is an okay groove. And what I might do is take this O-ring right here and hide it so it's not in there. And so the first thing we can look at is, what is the depth of the groove from here to here? 0.107. So there it is. And we go over here on the 200 level, and they get a gland depth of 0.107. So we're okay on the gland depth. And then the next thing is trying to figure out somehow there's a way. Oh, there, okay. So there is the that's this radius. All right, I'll try again. And so if we do this in SketchUp and we touch this curve using the measurement feature of SketchUp, this gives us the beginning of that radius to that curve. And that distance from there to there is 0.05, which would be 0.005 because this is times 10. And we can go back over into your PDF file. Or actually, we can just go look right over here, and it says 0.005 is okay. So this little curve right here is 0.005, which agrees with what they're telling us that we can do. Then we go down here to this curve, and this curve is R, and they give us a value for R on this size is 0.01 to 0.02. So now we got to go measure this. And so again, we can put this there, and we can put this here, and we can measure from here to here. 0.0, so that's 0.2. So, and they're saying 0.02, and over here it says that 0.02 is okay. So we're all right on this curve. It just goes on and on like this. And now the next thing we want to do is get the width of the groove, and that width is 1.86. So let's go look at the width. 1.87. So we're okay. And this is the complexity of what you have to go through if you want to do this in a way where the people who make this stuff say this will work out okay. And that is the only reason I did it this way. Is complicated. All right, so let's get that done. Oh, and I forgot to mention that this is squeezed down to 1.07. From really times 10, so it's squeezed down to 0.107, and it was 0.139. And if you take 0.107 and divide it by 0.139, it comes to 76%. So the amount of squeeze that we've done on this is 24%. And if you go over here, they tell you that the squeeze can go from 20% to 30%. So we're okay on that one too. Unbelievable, the complexity of this. All right, and we're going to get out of this micro level analysis and go to some other things. All right, so I can export that file out of SketchUp as an FBX file, and then I can import it into Maya. And there's a couple of things you need to do. Maya, there it is. Okay. And here are these two that I was just talking to you about. And there's a couple of things that helps us. Now, one thing is to set the preferences. Set the units to inches. And then the next thing is to take this material and make it a blend. And make it a little bit easier to see. Let's see. Okay, and then the other one is to take this material and make it a blend and get it a little bit darker so that you can see it. Now this is, I'm just putting this in here because there's a access port here for that 1/8 inch national pipe thread fitting. And so that's just something that like this one, well, I don't know how to darken that one, but oh, and the other thing is if you knock down the brightness in Maya and the gamma, things begin to be much nicer. So there it is, okay? And here is this one down here. So this is the one that's not clamped together. And down below is the one that is. And I think if you do a measurement from, for example, here to there, well, I can't quite see that. Oh, I know. I'm just showing you that it does import into Maya as it should. And it imports into there with appropriate fidelity to sizes. So let's see what this measures at. .96, so that's close enough. In other words, it's almost perfect, unless I didn't get these vertexes right. But you should be able to measure things inside of Maya. And I did do it, and I hate to be so hesitant, but I don't use Maya. I think Maya is a wonderful program. It just requires, there's a learning curve. Let's see what we get for this one. .96. So the scale has changed a touch, but at least it brought it in correctly where you can see it. And I did it before, and the scale was perfect. So it might be that I'm not doing this right, but it does pull it into Maya, and all the little parts get pulled into Maya, and so you can open these parts up in your drawing program. Because I think if it opens up in Maya, in Autodesk, it will open up in your drawing programs. Again, you'll see that I changed the opacity of the material so you can see through it to see what's going on. This is the cylinder end cap on the end that doesn't have the piston rod. And I put this little piece of metal here so you can, I might drill a hole in this. This is solid. And whatever type of in connections you want to put on this thing, you just slide it over that and you put a bolt through there. That's what I was thinking. And this is all inside of Maya. And so here, so here you see, let's and I'm going to go back into SketchUp because I'm just more comfortable with SketchUp. But we made this notch in the Delrin, and then this thing sticks its little teeth. Those teeth, I didn't want them to be sharp because it will cut someone's hand. They're only 1/32 of an inch wide. That's pretty small, and they are bolted on, and so these grab onto this, and when you pull this against that, the reason this can be pulled against that is because this is bolted to that. And this concept of how this works is over here. All right, so let me select this. Okay, and all right, so you can see that this thing that's grabbing onto the Delrin is being held against this thing by these bolts. These are 1024 bolts. And the accuracy of alignment is determined by the structures inside. And so this 1024 bolt is a 0.19 diameter, and the holes that I put in here are 0.22 in diameter, because I don't want to take these bolts and be fighting to get them to go through there. So these are not going through here in a manner where their objective is to perfectly align this thing. That alignment is caused by this Delrin being pushed up against this. So that's important. All right, so enough of Maya. All right, and we're back out in SketchUp, and this is the drawing showing it. And it is actually going to be very important. There's going to be a piston in here, that this is lined up because of the tightness of these dimensions. And if these bolts that are holding it together are not perfectly aligned, there is a possibility, I'm going to have to think about this, but I feel there's a possibility that we may have to I put this up here just to help it come together, but it could be that this is going to need to be modified. To be this condition. And the purpose of that will be if this is touching this edge, then that holds it perfectly aligned, which is sad because it makes the accuracy of these to be much more critical. And I'm going to have to think about it. It just may be that I have to do that. We'll bring this down a little bit. Well, it's not easy to fix this. But anyway, this curve will probably need to be more like this. But I'll get that. This is a preliminary movie anyway. But that, if that was touching, and I would make this maybe 1/1000th of an inch larger, because when they're absolutely exactly right on, it's been my experience, I don't know, you wind up with parts where you can't get it to go together because something is slightly off. I don't think 1/1000th of an inch is going to make a difference, or 2/1000ths. But that's something to consider. All right, and so now we'll take a look at how this all goes together. Oh, now, and I wanted to show you I went in there and I drilled the holes through, okay? So there's a hole that goes from here to there. And so that bolt is in there, and this orange thing has grabbed onto the Delrin. Okay, it's grabbed onto the Delrin, and then when you pull, when you take these bolts and pull the purple against the orange pulls in the Delrin. So that's something that, that's how that works. And the other thing I wanted to show you was, and I think I've already demonstrated some of this, but this also has a hole in it here to allow one of these bolts to go from here to here. So the first step that you do is you take this orange piece and you put it on the dowel ring. There's two pieces of, one that goes below and one that goes above, and then you put the bolt in there and bolt it together. I think I've already shown you that. All right, and so I drew that in for you real quick. This is another one of those brass hex head bolts with the stainless steel nylon insert lock nuts, and they will be on one here and one here, and they squeeze this upper part against this lower part, and it takes these little 1/32 inch wide ridges and pushes them down into the dowel ring. So that's the full device. And the other thing, this is what we call a split gland. So this is pushed up against that by these bolts, and we have to be careful that when we put this in with respect to the angulation of it, that you don't wind up with this or that. It has to be sort of, there's a short list of where this can go so that it works like it's supposed to. Because this comes down and curves around so that you can bolt this second half of the gland to the first half of the gland. That's the purpose of that design. And this is how I did this. You just, here is what that copper or brass pipe is going to look like. And I actually felt like probably you need to take your CNC machine and grind in a flat first. And then you take and this is not a National Pipe thread. This is just me making something that looks like a thread, but that's what you cut in there. The National Pipe thread is tapered. And this is just, there's all sorts of stuff like this on the internet. Hopefully your system creates a National Pipe thread without any issues, but the National Pipe thread, they've kind of exaggerated this, but the male has a taper to it and the female has a similar taper, but they're not the same. So that as you take the male National Pipe thread fitting and screw it into the female National Pipe thread it begins to tighten up so that it becomes water or fluid tight. And so National Pipe thread, that's what this is. And the other thing to show is on the other side of this, so this is the one that has this seal for the piston rod, but on the other end is another seal that just seals it up. This and this are the same. You can see that I did not match this up quite right. I was hurrying. But it's the same principle of how it works. The internal mechanics of this static seal over here is the same as over here. And this has inside of it a 1/8 inch National Pipe thread fitting so that you can introduce hydraulic fluid into this side also. And this has, I would probably going to put a 1/4 inch hole in this so that you can take all sorts of different connectors and just put them on there. All right. The one thing I need to discuss is that a static seal is where one structure is not moving with respect to the other structure. That's a static seal. This is a static seal, this spacer. But a dynamic seal is where one thing is held still and the other thing is moving. And So this piston rod shaft moves past this seal. So that's a dynamic seal. And this spacer is a static seal here, a static seal there, a static seal there, and a dynamic seal there. And so there's all sorts of specifications about surface roughness. Interestingly enough, I was not able to find any specification of whether there can be a corner radius on this spacer, or whether if this is listed as being 0.375 inches from here to here, are you supposed to have a little extra space in here in this groove so that this fits in there? I was not able to figure that out. I'm hoping I can buy some of this and send it to you, and you can measure it with your calipers. In your PDF, it shows here in your PDF that I sent you, it's page 18, and this is from Halide, a radius of 0.2 for this internal turn on the bearing. And they list the width of it, tolerances, as minus 0.1 to minus 0.1 to minus 0.5. That's probably millimeters. This is listing the RA that they want on the piston rod surface of 2 to 8 microinches. The RA that they want on the static sealing face, the back of it, is 63. And on the static housing faces, down the sides of it, is 125. Surface roughness RA values. I'm sorry, that was polytetrafluoroethylene. For the rubber, again, for the face of the piston rod, that can be 4 to 16 microinches RA. And again, the static sealing face up here can be 63 RA, and the sides of it can be 125 RA. And you can see that this is page 13 of your PDF. And this is going back and forth between page 4 and page 4 and page 3 of your PDF. This is the 605 Halide 605 rod seal polyurethane. And these are the faces. Again, this is the piston rod, 4 to 16 microinches, 63 and 125. And then there's these two radiuses for the groove of the halothane seal. And that would be this radius and that radius. And it looks like the way this is drawn, the pressure is coming in this way. So that's where the pressure. And so there's R2 and R1, and we go back to page 3, and R2 and R1 are shown as all right, well, I think, okay, so let's talk a little bit about, there's sections of this that are what I call optional. All of these dimensions are pretty concretely specified, but these curves I put in here, I just thought that was a good idea. This thickness I put in here seemed like a good thickness to me. I think this is times 10, so this is 0.3 inches. I thought we should have some thickness in here to make this thick enough, because it has this pipe thread, so it's 0.6 inches. Again, this thickness here is 0.35 inches, and this thickness here is 0.36 inches. And these curves are curves created by me that I thought just looked okay. I don't know if they need to be fundamental. This curve here is that 0.061 that they specify for the dynamic valve chamber groove. This curve, I think, is optional. I'm trying not to put surfaces on here that will cut anybody's fingers. For example, this 0.06 radius can probably be down here too. I forgot to put that in there. On the other end, the okay, I drew, this is the other end cap, but it's drawn facing that way because I was using this drawing because this part of that is the same. So this entire other end cap is drawn facing that way, and at the very end of it, I mean, if I want to, you can just take this in SketchUp and make this -1. And it flips it so it points in the other direction. And that's all that this is. But this entire structure here, the purpose of this structure is to seal it up, and also to have, like, for example, all of these curves are just by me. And this thickness is enough thickness to put this national pipe thread in there, and this opening down here is just an opening so that this can get in there to let the fluid go into it. And this little knob that sticks out is just enough of a knob that you can put various different attachments on here to the end of the other end of the hydraulic cylinder. And of course this is going to be, this will be the same on either end. So either end of the Delrin tubing, the connectors on the end of it that grab onto the Delrin tubing, they're going to be the same on either end of it. So this connector, this orange connector here with these 2 bolts in it, that will be the same connector on this end, and it'll just be flipped and be the same connector on that end. And that's what I'm trying to show with this drawing. And I just split it. Okay, well, that's probably enough. I will send this to you as a video, and I'm going to work on these a little bit and make sure that I get it just exactly the way I want it. I'm beginning to think that I have to move this down, and I'll be interested in your judgment on how much bigger this should be than that, so you don't wind up making a structure where you can't get it to go together because it's too tight.